This is geometry 6.2, bisectors of triangles. Before we talk about the bisectors of triangles, we need to go over a few terms or definitions. And one of them is concurrent, either concurrent lines, rays, or segments. We'll specifically just talk about concurrent lines right now. So concurrent lines have to be either three or more lines that intersect in a point. So for example, I have line L here, line M, and line N. If all three of those lines intersect in a single point, those three lines are concurrent. As I mentioned, you could also have concurrent segments. You could also have concurrent rays, but we'll just concentrate on concurrent lines. And then the point where they intersect or meet is the point of concurrency. Whatever you want to call that, like point P would be the point of concurrency for these three lines. And then we'll talk about also perpendicular bisectors of a triangle. Recall that a perpendicular bisector of a segment is a segment, could be a line, it could also be a ray that cuts a segment into two congruent parts and is also perpendicular to that. So each of the sides of the triangle, I'll label this triangle ABC, are segments. I could find and create the perpendicular bisector of each of the sides of the triangle. Okay, one thing that we need to do with each of the sides is find the midpoint. So the midpoint of AC, I'm just going to kind of eyeball things right now. I'm not going to use a ruler or anything else. But to show that this point's the midpoint of side AC, I could use tick marks. That means this segment is congruent to this one. Do the same thing with side BC, and then do the same thing with side AB as well. Find the midpoint, and then I can make a perpendicular segment through each of those midpoints. So for side AC, again, I'm just kind of eyeballing things here. A perpendicular segment that's at a right angle, and then this shows that it's at a right angle. Do the same thing with side AB, and then lastly, do the same thing with side BC. If I did everything correctly here, I kind of eyeball things, so it might not appear that all three of those segments or all three of those perpendicular bisectors intersect in a single point, but they do. So the three perpendicular bisectors of a triangle are concurrent. I know I just used one example of a triangle here. It might appear that the triangle is obtuse. I could have used an acute triangle. I could have used a right triangle, equilateral triangle, isosceles. It doesn't matter. If you construct or create the three perpendicular bisectors of a triangle, then no matter what kind of triangle you have, those perpendicular bisectors would meet at a single point. So they're said to be concurrent. Here's the point of concurrency. That point of concurrency for the three perpendicular bisectors of any triangle has a specific name. Okay, that name is called the circumcenter of the triangle. So the circumcenter of a triangle is the point of concurrency specifically for the three perpendicular bisectors of a triangle. Any triangle has three sides, so it would have three perpendicular bisectors. As you'll see, once we start talking about other points of concurrency for triangles made up of other segments, all of them have specific names. So one of the names is the circumcenter. Again, the point of concurrency of the three perpendicular bisectors, or just the perpendicular bisectors. It's really implied, or you should know that there would be three of a triangle. So this leads to theorem 6.5, the circumcenter theorem. So the circumcenter theorem states the circumcenter is equidistant from the vertices of the triangle. Now, that's definitely true, but here's why. If I create each of the perpendicular bisectors of the three sides of this triangle, PQR, here's the midpoint of PR, and then here's a segment that's perpendicular through the midpoint, so that's the perpendicular bisector. I can repeat the process for side QR. And lastly, for side PQ, hopefully you'll be able to see this color. But all three of the perpendicular bisectors meet at a single point. Again, that's the circumcenter. And the reason why the the circumcenter theorem works, or the reason why it's true. If you just think about each of the segments that make up the sides of the triangle, remember the perpendicular bisector theorem? If a point lies on the perpendicular bisector of a segment, then it's equidistant from the endpoints of the segment. So if I just take a look at this point, the circumcenter, I'm going to label it here. For side PR, if I just think about that as a segment, which it is, but kind of ignore QR and QP right now, this point is equidistant from the two endpoints. So these two distances would be the same. The circumcenter is also on the perpendicular bisector of side QR. So since it's on the perpendicular bisector of that side or segment, it's equidistant from the endpoints of that segment, R and Q. And then the same thing is true for the perpendicular side bisector of QP. Okay. The distance of the circumcenter from the endpoints P and Q would be the same. So these three distances from the circumcenter to each of the vertices, P, R, and Q of the triangle are the same. Again, the circumcenter theorem really follows the perpendicular bisector theorem.